We're going to start with a square with the area 4, and then we're going to clone this square 2 times, and we're going to align all our squares horizontally so that their sides are touching, just as shown in the sketch. Next, we will pull the diagonal from the upper left corner of our left square to the down right corner of our right square. And from the upper left corner of our left square, we will pull another line which is perpendicular to this diagonal. Then finally, from the down right corner of our right square, we will pull the diagonal which we will extend to our previously constructed line, therefore forming this really nice red right triangle. The question is, can we somehow calculate the area of this red right triangle? This viral problem was presented to me by one of my subscribers, Herbie, who wanted to see my take on it. So thank you, Herbie, for this interesting challenge. Well, if you want to try this one for yourself, you can pause the video right now and then come back and check my solution. Alright, so let's solve this one. So when I was preparing for this problem, I found 7 different methods to solve it. Some of them included analytical geometry and some of them included trigonometry. But today I'm going to present you 2 different methods which are not using any of those. And the second method will be quite interesting one because I'm going to even try to avoid Pythagorean theorem. Alright, so let's solve this one and let's start with the method number 1 of using the geometry. First, we know that the area of our small square is equal to 4, and since the area of the square is equal to the side squared, we can easily find that the side of our small square must be equal to 2, so we're going to first label all those sides. Next, I'm going to label all the vertices of our right triangle as A, B, and C. Then I'm going to label the intersection point between the hypotenuse and the upper left corner of our right square as D. Now I'm going to pull the height of our right triangle from the vertex C and label its intersection with the hypotenuse AB as E. And finally, I'm going to label the down left corner of our left square as F. Great, so now let's start solving this problem. First, let's take a look at the line BD. This line is actually the diagonal of the square, so this means that it will form the 45-degree angle with our blue horizontal line FB. But since we know that DE is actually an extension to this diagonal, this means that the line ED must also form 45-degree angle with the line CD, since the lines CD and FB are parallel to each other. With this in mind, we can take a look at this right triangle CED. Since it has the acute angle of 45 degrees, this means that the other acute angle must also be 45-degree angle. So this triangle is actually an isosceles right triangle with the hypotenuse CD, which has the length of 2 times the side of the square, and that is equal to 4. Now, since this is an isosceles triangle, this means that the lines CE and ED are identical. Now we will use the formula for the diagonal of the square, which states that the length of the diagonal of the square must be equal to the side of the square times square root of 2. And we're going to use this formula in 2 cases. First, we're going to use it to find the length ED. Since the triangle CED is an isosceles right triangle, it must represent the half of the square with the diagonal CD and the side ED. So, if we substitute the value of the CD, we can work through this and get that ED must be equal to 4 over square root of 2, which we can rationalize to 2 square root of 2. Great. Now, let's have a look at the line BD. It is also the diagonal of our small square with the side 2, so DB must be equal to 2 square root of 2. And now, as you can see, all our red lines have the same length of 2 square root of 2. Now, let's continue by taking a look at the line CB. You can calculate this line as the hypotenuse of the right triangle CEB, or you can calculate it as the hypotenuse of the right triangle CFB. Today I will use the right triangle CFB. So, the hypotenuse CB squared must be equal to the leg CF squared plus the leg FB squared. Now, we're going to substitute our values and work through this to finally get that CB squared is equal to 40, which means that CB must have the length of square root of 40, and we can simplify and say that CB has the length of 2 square root of 10. Alright, so now we will use one really interesting property of the right triangle, which states that the height of the right triangle drawn from the right angle vertex divides the right triangle into two similar right triangles. We will use this property on our right triangle ABC. Since the line CE represents the height drawn from the right angle vertex, we can clearly divide our big triangle into two small right triangles which are actually similar to each other. So we can use the rule of similarity on those triangles. We can see that the relation between the sides EB and EC of our two triangles is equal to 4 square root of 2 over 2 square root of 2, which we can simplify and get that this relation is equal to 2. Since those two triangles are similar, that means that the sides of our bigger green triangle are actually twice as big as the sides of our smaller blue triangle. So we can easily find the hypotenuse of our blue triangle AC. We can just divide the hypotenuse of the bigger triangle with 2, and we will get that AC is equal to square root of 10. Now it's easy for us to calculate the area of our red triangle ABC. Since it is the right triangle, its area must be equal to the half of the product of its legs. So we can just substitute the values of CB and AC, we can cancel 2's, and finally get that the area of our red right triangle is equal to 10 squared units, and there we have our solution. Alright, so now let me show you a second method, which is really interesting one because I'm not going to use Pythagorean theorem to solve it. So we are going to start with the fact that the area of our small square is equal to 4, so we already know that the sides of all squares are equal to 2. Next, we are going to do some out-of-the-box thinking. We're actually going to put the frame around our triangle so that we will basically get the right triangle which is inscribed into rectangle. Now let's take a closer look at the upper left corner of our rectangle. We can see that we have another right triangle there, and we will label its legs as X and Y for the time being. Next, let's notice another right triangle to the bottom of our rectangle, which will have the legs of 2 and 6. Now, let's take a look at the acute angle of this bottom right triangle. We can label this angle as alpha, which means that the other acute angle must be equal to 90 degrees minus alpha, since this is the right triangle. But since this angle and the 90-degree angle together form 180 degree with the acute angle of our upper blue right triangle, this will lead us to conclude that the acute angle of this upper blue triangle must also be equal to alpha, which in fact means that our blue and green triangles are actually similar. So we can use the rule of similarity. We can say that the relation between their legs, x over y, must be equal to 2 over 6. We can now cross-multiply this and get that 2y is equal to 6x, and if we simplify this, we will get that the y is equal to 3x, so we're going to substitute this value for y. Now, we will take a look at the right side of our rectangle. There we will find another big right triangle. And you can see that the hypotenuse of this triangle is actually an extension to the diagonal of the square. And since we know that this diagonal forms a 45-degree angle with the side of the square, we know that one angle of this triangle must be 45-degree angle. But since this triangle is the right triangle, we know that the other acute angle must also be 45 degrees, which means that this purple triangle is actually an isosceles right triangle. Now we will calculate the legs of this right triangle. We will take a closer look at the base of our rectangle with the length of 6 and the smaller leg of our blue triangle with the length of x. And if we slide this base upward, you can clearly see that the leg of our right triangle must be equal to the difference between 6 and x. Now we can find the length of the right leg of this triangle as the sum of 3x and 2. Now, since we know that this triangle is an isosceles right triangle, that means that both of those legs must have the same length. So, 3x plus 2 must be equal to 6 minus x. We will use this equation to find that 4x is equal to 4, which means that the value of x is equal to 1. Now we will implement this value into our sketch and calculate all lengths. Now you can easily calculate the area of this triangle by using the Pythagorean theorem, but like I said, I'm not going to do that. So I will first label all the areas of our colored right triangles as A1, A2, and A3. Then I can say that if I take the sum of all the areas of those triangles and I subtract this sum from the area of our big rectangle, I will actually get the area of wanted red triangle. Since all our triangles on the sketch are right triangles, we can use the fact that their area is equal to the half of the product of their legs. So for the area of the purple right triangle, that's 5 times 5 over 2, which is 12.5. For the area of the small blue triangle, that is 1 times 3 over 2, which equals to 1.5. And for the area of the green triangle, that's 2 times 6 over 2, which is equal to 6. And finally, the area of our big rectangle will be equal to the product of its base and the height, which equals to 30. Now we are just going to substitute all our values into our previous equation and get the following. Here we can simplify and get that our red area is equal to 30 minus 20, which means that our wanted red area is equal to 10 squared units, and again we have our solution. Like I said at the beginning of the video, you have a lot of ways of solving this problem, so you guys can be super creative when you try to solve this one, and I cannot wait to see your solutions down in the comment section below. Of course, if you enjoyed this video, please leave a like and consider subscribing to the channel for more content like this in the future. And of course, until next time, see you all and take care.